now, what I want to present where we are now is actually highly significant in statistical theory of hypothesis. And that is why I wanted to pay attention. If you don't understand or ask question, Neyman and Pearson actually work together, and they work together. They were actually looking for the most powerful test. It's just like I'm looking for the most powerful court. The most powerful court is a court that has, number one, has a territorial jurisdiction to answer a case. Even if you have the best court and the court does not have a territorial jurisdiction, then it's not best court, because whatever they decide would be declared null and void, because the court doesn't have territorial jurisdiction to answer the case. Now, what make a court? Before we can actually say a judgment from a court is laudable or most powerful judgment. Number one, it must have a territorial jurisdiction. Number two, whoever that is accused must be given a fair hearing. Number three, of course, they have to be using the best threshold to judge the accused. Because of that, we're going to say whatever judgment coming from such courts is actually going to be laudable and is going to be most powerful. Do you know why Neyman and Pearson actually work together? Because they know that whenever we are conducting hypothesis, we normally face with two types of errors: the type 1 error and the type 2 error. Of course, we've done that in this class. And in this class, I've been able to show that when you make an attempt to improve on one of the errors, of course, it's actually going to affect the other one. And I told you the other time that, okay, you know what, the only way we can minimize both errors is actually to increase our sample size. But don't also forget, it's not easy increasing our sample size. It's actually going to spend more money, because the more people you interview, the more the resources you're going to commit, the more money. And don't forget, we are limited by budget. Now, how are we going to get the most powerful judgments? I mean, most powerful tests, given those restrictions. And that was why Neyman and Pearson, actually give us a way out by means of a likelihood ratio test. Okay, they gave us a powerful and highly principled way of constructing our hypothesis, and they were able to arrive at that because they actually optimized the trade-off between type 1 and type 2 error. If we are able to optimize the trade-off between type 1 and type 2, then your test is going to be most powerful. And I want to show you the significance of this is that at the end of the day, uh, if you consider so many, given a specified level of significance, of course, they are able to minimize, type 2 error, which means they were able to maximize the probability of correctly rejecting the non-hypothesis. Maximizing the probability of correctly rejecting the non-hypothesis is what we call the power of a test. Because the power of a test is ability to take correct decision, rejecting the non-hypothesis when it is wrong. That is what we mean. Now, because of the fact that in this class I've walked you through likelihood, you're actually going to be fine, because when you have any distribution, if you're able to get a likelihood, then all what you're just going to do, if I want to go by Neyman Pearson Lemma, I only need to derive two likelihood. The first likelihood is actually going to be based on the non-hypothesis, okay, which is going to be the one here, okay? We're still talking about the same probability, distribution. We're going to have the same distribution in the known. We're going to have the same distribution in the alternative, except that the parameter we're plugging in is what make the two likelihood to be different. Now, the Neyman and Pearson prove, they establish the most powerful test using the likelihood ratio test. They believe that the likelihood ratio test will be most powerful for testing this hypothesis under certain conditions. Now, is there anyone who doesn't understand, that? Is there anyone who doesn't understand that? Okay, now, and you know what? The condition they gave is this. This guy has to be less than a constant C. If that guy is less than a constant C, we're actually going to reject H naught. Otherwise, we're going to fail to reject that. So which means, what is our C? We don't know our C. So that varies the values of the C we need to be choosing based on the desired level of alpha. The alpha here is what I call the maximum probability of committing type 1 error. Okay, so take a look at that. Okay, so that's what we call the likelihood ratio test, because it involves the ratio of the likelihood. Okay, our intention is, if I'm able to maximize the power of my test, then my test will be the most powerful. Does that make sense? And if I'm able to, in other hand, if I'm able to minimize the probability of type 2 error, because 1 minus the probability of type 2 error is the power of a test. So which means, if I minimize the probability of type 2 error, then I've succeeded in maximizing the power of a test. That's what it means. And we're going to do that, okay, given the probability of type 1 error, because in every test, we're always going to disclose our level of statistical significance. Now, I want to define the power now. What do I mean by power? Okay, the power, the probability of W, if W is a test statistic, okay, if W is a test statistic, the probability that W actually fall in rejection region when the parameter value is theta, okay, which means we are correctly, rejecting the non-hypothesis. We are correctly, rejecting the non-hypothesis. We reject the non-hypothesis because we believe it's false. We believe the alternative is good. That was why. Okay, now take a look at this now. We want to figure out the power. Okay. Like I said, we are actually testing. We're testing that somebody claimed theta equal to theta naught. And we said, no, it is not equal to theta naught. If it is not equal to theta naught, maybe it is theta A. It could be something else. That's what we mean. Now, we're seeking power. But no matter what we do, we may not get 100% power. It's not possible in a stochastic world. Okay? Because there's always going to be level of significance, right? The probability of type 1 error, right? Okay, so now, when theta equal to theta A, that A means, the values of the parameter under the alternative. Does that make sense? Your theta naught is the values of the parameter under the non-hypothesis. Okay, so we now want to seek to determine the power now. Okay, whenever we want to determine power, it's going to be a function of the values under the alternative. Okay, so which is the probability of rejecting H naught when theta is equal to theta A, which means when the alternative is true. Then I have to reject the null. That's what we call the power. Okay, now, do you know the opposite of that? Okay, so which means we can maximize that. That's our intention. And if you take a look at this guy on the other hand, is the probability of accepting that H naught when theta is actually theta A and not even theta naught. So, which means what we're actually going to do is, if I can minimize the probability of type 2 error, I have automatically succeeded in maximizing the power of my test. Does that make sense? And that's exactly so which means relationship exists between the probability of type 2 error and the power of a test. And this is the relationship. Take a look at that. They are inversely related. Okay. The lower the probability of type 2 error, the lower, then the higher the power. Does that make sense? So if I give you an exam and I ask you to find what is the power of a test, you can for first find the probability of type 2 error if you want. Then you subtract that from 1, and that will give you the power. And you can also go direct to figure out your power. There's no problem. Okay? So take a look at that. Now I want to give you another example now. I think this is a further example on simple and composite tests. Of course, I've walked it through when you have this guy, I told you the other time, that would, by the time you plug that in, okay, that's for simple hypothesis. Okay, that's going to be called simple hypothesis. But if you have that greater than 2, okay, then that's going to be called composite. I think I'm just trying to give more example on that. Okay, so I think I'm going to move right now. Okay, and this another one. I think I've talked about this as well, when you have a normal distribution with 2 parameters. Okay, if you take a look at this guy now, sigma square is known to be 1, and the non-hypothesis mu equal to 5. That would be simple because the variance is known. Okay, but situation whereby the variance is not known, okay, even though the mu is is hypothesized to be that value, the fact that one of the parameters is unknown, that make it to be a composite. Now let me tell you this. The idea of Neyman Pearson Lemma, that is the likelihood ratio test, can be used for simple hypothesis, can also be extended to composite hypothesis. Does that make sense? Okay. Now I'm going to move right now. Okay. Now, if you take a look at this, suppose we would like to test a simple non-hypothesis. So whenever you see something like this, okay, we actually have provided the distribution does not have more than one parameter and the other one is unknown, it's going to be simple hypothesis. But if the distribution has another parameter that is unknown, there's going to be a composite. But right now, it's simple. I just wanted to know that. So if I want to construct the best critical region, or I want to construct the most powerful test as given by Neyman and Pearson, then I need to look at the distribution. Then I need to get the likelihood of the distribution. Okay, when I get the likelihood of, and that is exactly what I'm trying to talk about here. Take a look at this. I will need to first get the likelihood of the distribution. Okay, you can see a lot that we've been doing here involve getting likelihood. I remember when we're trying to get sufficient statistic through Neyman-Fisher factorization. I think we also get the likelihood. We factorize that. And I also when we're looking at the Pearson Lemma, okay, we also get the likelihood. And I remember when we're working on the method of maximum likelihood, we also get the likelihood of a distribution. I want to believe you are used to getting the likelihood of a distribution, because if I ask a question on most powerful test, okay, since that involves a likelihood ratio test, then you actually need to understand likelihood. Okay, once again, this is the Neyman-Pearson Lemma theorem. If I ask you to state a Neyman Pearson Lemma theorem, this is what I expect you to tell me. Okay, suppose we wish to test the simple non-hypothesis that versus the simple alternative hypothesis based on a random sample y1 up to yn from a distribution with parameter theta. Let L of theta denote the likelihood of the sample when the value of the parameter is theta. Then for a given alpha, that is for a given level of significance, okay, which we also call the level of statistical error, which we also call the maximum probability of committing type 1 error. Okay, so for a given alpha, the test that maximizes the power, I said it the other time, a test that maximizes the power, okay, it's actually what we call that, which we call it the most powerful test because it maximizes the power. And when it maximizes the power for a given level of significance, it means you know your level of significance, but you're looking for a way to maximize the power of your test. You can maximize the power of your test by trying to minimize the probability of type 2 error. Okay, and which is actually this. So when it is less than k, and that values of k can be found, okay, putting into consideration the level of significance, that we're actually going to call this the most powerful test. I want to walk you through an example now, and I need you to pay 100% attention because I'm already seeing some final questions. Okay, because the probability you're going to have a likelihood ratio test in the final exam is 1. And that's why I wanted to pay attention now. Okay, now suppose that Y represents a single observation from a population with a probability density given as that. I need you to pay attention. Okay, whatever distribution they gave you is representing just one observation. Do you know when you're going to have more than one observation? When you take the likelihood. Does that make sense? Okay, now take a look at this distribution now. The state space is between 0, 1. And you know what the question, you know what they're asking you? Find the most powerful test with significance level alpha. I told you, they're actually going to give you the level of significance. The level of significance is the maximum probability of committing type 1 error. Every researcher must disclose that. Okay? Now, and you want to test. What do you want to test? You actually want to test, we're going to test this guy. Okay? Under the non-hypothesis, in the distribution, the parameter is theta or is unknown. And we don't know it. And somebody now come with a claim that what is unknown is true. That theta is true. And we're now maybe we actually going to go against that one and say, no, it's 1. Okay. Now, how do we take a decision between this? We need to conduct a test, but we're not conducting tests. You know what we're doing? We're not making judgment, but we are curating. We're trying to curate the best avenue to take the best judgment. That's what we're doing. It's like, okay, you know what? Don't try that case, but give me the best cut for the case. That is what we're trying to do. Now, so find the most powerful test. Does that make sense? Now, to find the most powerful test, by Neyman Pearson Lemma, we need to get the likelihood. The likelihood of the false, the likelihood. So if you want to get the likelihood, but if you take a look at what I have here, because they say in this research, they are not taking more than one sample. I'm going to say that again. Let's say, for instance, the question read, let y1, y2 up to yn. It means they're taking a sample size more than 1. But in this question now, they actually said that, okay, we are only taking just one sample. That is why they say a single observation. Then for a single observation, the likelihood is going to be the same as the function given. I'm going to say that again. For one observation, we don't talk about likelihood. It's just going to be the same as the function given. But for observation more than one, then we can talk about likelihood. So in that regard, when you take a look at this distribution now, okay, take a look at this distribution now, okay, because we're talking about one observation, okay, my likelihood for theta naught, is actually going to be, what was under the non-hypothesis? Theta equal to 2, right? I'm actually going to write 2. I think that should be 2y because we plug in it to wherever you see theta. Any question about how I get L of theta naught equal to 2y? Okay, now what about getting L of theta A? Okay, getting L of theta A. What is the value under the alternative? 1, right? Okay, I'm going to plug in 1. Okay, when I plug in 1, I think the whole thing is going to be 1. Any question? I've already secured the likelihood. Okay, and I said I'm not using the joint PDF here because they mentioned 1 observation. What am I going to do according to Neyman Pearson Lemma? I'm going to find the ratio. That's going to be 2y divided by 1. That is why we have this. What is 2y divided by 1? What is 2y divided by 1? That's 2y, right? Take a look at that. I also already got 2y. Any question? And the ratio, according to Neyman Pearson Lemma, the ratio is less than k. Whatever we get, we're going to say less than k. When you are done with the ratio, you're going to say less than k. Don't forget, less than k implies that you reject the non-hypothesis. Okay? Now, take a look at this now. That was why, and now I'm now going to say, and the form of the rejection region for the most powerful test is going to be 2y less than k. Let me tell you this. You're only going to have the best cut if you have the best threshold that you use in the court to judge. We're only going to have the best test if we have the best critical region. If we have the best rejection region, that's what I mean. Okay? Then you're actually going to have the best judgment. Now, 2y less than k, then I'm going to solve for y. When I solve for y, okay, I'll be able to get my rejection region. What is that? I'm solving for y, divide both sides by 2. That will be y less than k over 2. That is the rejection region. So what we're trying to tell the world, if they want to test that hypothesis and they use this rejection region, because this rejection region is the most powerful critical region to be used to guarantee the best test, the most powerful test. Now, and k over 2, k is a constant, and k over 2, that's another constant. I can simply, because k over 2 is k star, I can simply say, okay, you know what? My rejection region is actually y less than k star, where k star is k over 2. Is there any question at this time? Okay, now you now know what I need to do. Then I need to figure out that k star. Now, if I want to figure out the k star I told you the other time, I need to put into consideration the alpha level given, the significance level. And because of that, that will take me to this guy. And I'm going to explain this guy now. Please pay attention, because what is the 0.05 we've been given from day 1? That is the alpha level, right? And what does alpha level represent? Alpha level represent the probability of type 1 error, which is going to be the probability that y, don't forget, your y less than k, this is your rejection region, okay? So what is the probability that y falls in the rejection region when theta equal to 2? Where do we see theta equal to 2? For in the rejection region, which means when the non-hypothesis is true. Is it, this is a non-hypothesis, right? Okay, your probability of type 1 error equal, the probability that, The test statistic falls in the rejection region when the null hypothesis is true, and when the null hypothesis is true, when theta equal to 2. Does that make sense? Okay, now take a look at that now. And don't forget they've given me 0.05. I'm just going to equate it to that. What am I going to do? Oh my God, I need you to pay attention now. I need you to pay attention now. I'm going to bring my rejection region in. Okay, let me first do this. You see this? And what is my rejection region? What I derived. If this guy is wrong, this what you want to do here is going to be wrong. That's why you got to pay attention. Now, any question up to this moment now? Any question up to that moment? What am I bringing in? I'm bringing my rejection region. The rejection region that I derived using Neyman Pearson Lemma. Then what am I going to do now? I want to find the probability of y less than k star. This is going to take you to star 4101. Okay, what is the probability? I now want to make use of the distribution. Okay, I'm going to go from the lower to k star. And what was the what was the lower bound in the distribution? Can you see that, right? 0 to 1 is going to be 0 to k star. Okay, then in the distribution, okay, I'm going to plug in when theta equal to 2. Why am I saying theta equal to 2? That is a non-hypothesis. Don't forget we are trying to find the probability, okay, that the non-hypothesis will be rejected when it is true. That's why I'm using that. So 2y to y, when you integrate that guy, you're actually going to have 2y squared over 2, which is going to be y squared. Then you plug in k star and 0, you subtract, that will automatically give you this guy here. Any question? That will be k star squared. Okay, now after getting that k star square now, you're now going to write, you're going to equate that k star square to what? The level of significance given. They've given you 0.05. Mathematically speaking, you'll be able to get your k star, right? What is your k star now? Okay, that's going to be square root. If I have this and I want to get my k star, okay, my k star is going to be square root of 0.05. Okay, finally, this is my rejection region, which means R less than 0.2236. When R is when my test statistic is less than 0.2236, I will reject the non-hypothesis. That is what that means. Is there any question? Now we figure that guy out. Now, because in the same question, what is the power? We want to figure out the power now. Okay, if I want to figure out the power, take a look at this. What is power? If I want to figure out, I say power in 1. Okay, if I want to figure out power, we have to consider the value of the theta under the alternative. What was the values of the theta under the alternative? Okay, the values of the theta under the alternative is actually 1, right? And so if I want to talk about power now, okay, that's why you say power into 1. That means power when theta equal to 1, the value in the alternative. Now, what is the probability of y in the rejection region when theta equal to 1? Why do I say that? Okay, that's a good one. Okay, the y falls in the rejection region when theta equal to 1, which means I will reject the null because theta is 1. And where is theta equal to 1? It's in the alternative. That's a correct decision. Does that make sense? Okay, now what I want to do now, if I want to calculate power, which means you cannot calculate power, I mean, your power is going to be wrong if your K star is wrong. Your K star was 0.2236. We computed that. Now, right now, take a look at this guy. I now want to find this guy here. Take a look at that. The probability of y less than 0.2236 when theta equal to 1. Imagine if your K star is wrong. Okay, the net, because you want to use that in power now, that's going to be wrong. Now, I now want to find what is the probability of y less than 0.2236 when theta equal to 1. You know what I'm going to do first? I'm going to go back to the distribution. When theta equal to 1, I'm going to plug in 1 for theta. And after that, less than 0.2236, I will be coming from 0 to 0.2, which is this guy. Any question? You know what has happened now? Because it's going to be 1, the distribution when you plug in 1. And when you integrate, it's going to be y. And plug in that minus plug in 0 is still going to be giving, it's going to be that. And what has happened here? The power is very, very small. This is not the power we're anticipating. Because you know why? The power is very small. The type 2 error is so huge. Because 1 minus this guy is type 2 error. Type 2 error is 0.7764. You see that? That is so huge. And do you know the reason for this? You know why this happened? Because you only consider one observation. Does that make sense? You only consider one observation, even though you specify lower value of level of significance, but you got a huge power. And this is the reason why you shouldn't just focus on one observation. And that is the reason. Does that make sense? That's what we mean. Okay, now I'm going to go into another example now. I want to go into another example now. And I need you to pay attention. Suppose that y1, y2 up to yn constitute a random sample from a normal distribution with unknown mu and known variance. Variance is known and unknown mu, and mu equal to mu norm, mu greater than mu naught. Mu greater than mu norm may be mu equal to mu a. Okay, this is going to be a simple hypothesis. What are you going to do by, and they ask you to construct, find the uniformly most powerful test with significance level alpha. Okay, of course, we are working with a normal distribution. Okay, what are we going to do? We actually, because they mention, come back here now. What do you see? They're taking a sample more than one. Pay attention. Y1 to yn. Then the likelihood, the likelihood now is going to be a joint. And this is the likelihood of a normal distribution. If I were you, I need you to, understand likelihood of probability distribution. This is the likelihood of a normal distribution, which is the joint of the individual one. Then what am I going to do next? I'm going to get to likelihood, okay? And I'm going to plug in mu0 and mu1 going by this. Do you see this guy now? In the likelihood, I'm putting mu0, which is the values under the null hypothesis. In the alternative, I'm putting mu a. Now I'm going to say less than k. Oh my God, that is what I'm doing here. Any question? It's just the ratio of the likelihood. It's the same, except that in the numerator, it is mu0. In the denominator, it is mu a, which is the mean under the alternative. Is there any question? Now you need to do algebra. You need to know how to simplify. Okay, of course, this guy. Of course, this guy. It's actually going to cancel out. When you cancel out exponential, you can bring them together. Law of exponent. I'm actually going to have this guy here. Okay, that's going to lead to this guy. Okay, that's why you do math in high school. Now, the moment I have this guy now, okay, then I'm going to simplify. Let me tell you this. We're targeting mu, right? Then sufficient statistic for mu, right? Summation y. Okay, you're going to see it's going to play out here. At the end of the day, I'm going to start solving. Now, what have I done here? Here, because what I'm looking for, summation y is what I'm looking for. Sum of y, because whenever mean is involved for normal distribution, we need a summation y. You remember summation y was a sufficient statistic for mean. Then I want to remove exponential. I'm going to take the log of both sides. Okay, and that was why you see this guy here. You see that? Now have a lane at the other hand. We simplify. We simplify. Look at that. And at the end of the day, we got that to be y bar. Initially, you're going to get summation y divide by n. It's going to be y bar greater than that. Now let me quickly talk about this. This is a function of k, sigma square, mu naught, mu a, and so on like that, and even the sample size. But do you know that what you see here, what you see here is just a constant. I can just write it as this. My rejection region to be that, where rejection region is going to be y bar greater than the constant k. Look at that. Okay? And which is a condition to reject because I'm dealing with the normal. Okay? If I'm dealing with the normal, the interest will be on the y bar, right? Now, what I want to do now, I'm trying to say the most powerful test for this is using this rejection region. Okay? Now, because rejection region matter, now, you know what I need to do? Just like what I did the other time, because I want to figure out my K star, right? You remember that time we figure out K, and for us to be able to figure out K, we actually, four of us need to start from the probability of type 1 error, and after figuring out the K, then we go to the power of a test. We want to do the same here now. Okay, now what is that? Again, the probability of type 1 error is y bar force in the rejection region when mu equal to mu naught. And what are you going to put here? What you just derived. Is that not what you derived? Okay, you see what you just derived. Greater than, okay, you're going to plug it, you're going to put it here. You see that now? Okay, and that because of the fact that we're talking about normal, the idea of standardization, the z-score can be used. You want to find the probability of y bar greater, okay, than k, then you're going to use a z-score because here it's going to be the mean under the null hypothesis and the standard deviation, which is standard error. By the time you plug in that, what is going to happen? This guy here is a z, right? Which is this guy here, right? And if this guy is a z, if I want to rewrite this guy now, okay, the root 10 can go up, right? If I have that divided by sigma over root n, I can also have it like that. And if I have it like that, please pay attention. It's getting tough. Pay attention. Do you know that this guy, you remember we've done something like this, right? What does that mean? Z alpha is that guy. Do you see that? Z alpha is that guy because the probability of Z greater than Z alpha equal to alpha. And don't forget, the whole of this equal to alpha. So because of that, I'm actually going to say this. I'm actually going to say, okay, that guy, that is this guy here, is actually Z alpha. Then solve for K. When I solve for K, this is my K now. Do you know what I just need to do? I need to know the value specified in the null hypothesis. What I'm going to check from the Z table, the standard deviation, because they say it's known, and the sample size. You see that? That's what I just need. Okay. Now, okay. You know what? We're gonna have 4 more slides. Okay. I will finish this today on recording. I will merge it with this and I will share it because I want to make sure I finish this chapter today. So I only have this. Look at it. I have just one. That, that, I'm done. Okay. So I know where I stop. I'm going to make a record. I'm going to join that. And if you need more clarification, you can meet with me. Okay. Okay. This is where I'm going to stop because I think my time is up. Is there any question before I go? A little bit like serious in the way, but it's easy if you can follow the way we're doing it. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone. alpha level test, we have the largest possible value of for power. Okay, that's actually going to be based on statistical Y bar, and of course, we've been able to figure out the rejection region. So, because the rejection region is going to be Y bar greater than this guy here. So, uh, of course, we actually going to use this, in taking decision regarding whether to reject the non-hypothesis or to actually fail to reject that. So we actually believe, that for any specified level of significance, alpha. Okay, the rejection region that we have here is actually going to be the best in deciding on, whether to actually reject this, okay, or not. So that's exactly what we mean. Okay, so I'm gonna go into another example right now. Okay, so uh, maybe we're still talking about the underlying distribution is in a normal, and just like what we did the other time, um, the variance is actually known, and except that the values of mean is under contest. So under the null hypothesis, the mean is actually mu naught. Under the alternative, it's actually mu one. So the likelihood ratio test is going to be applied according to Neyman Pearson Lemma theorem. So by the time I actually do the ratio of the likelihood of a normal distribution and I simplify, I'm actually going to have this guy here. And, having this guy here, I'm going to simplify, okay, mathematically, putting into consideration, statistical terminologies. I'm actually going to arrive here, and you know that Neyman Pearson Neyman actually puts the ratio, to be less than C. Okay, so less than C right now. So if we go by what we did before, if you introduce lean to both sides, because this guy here, give me 1 second, just like what we did the other time, it's going to be less than C. Okay, according to Neyman Pearson Lemma theorem. Okay, so and we're going to take the the natural log of both sides and so for x bar. So we're actually going to have this guy. So the x bar greater or than that. Okay, so what we're trying to say, when you are testing in the non-hypothesis, mu equal to mu naught, in the alternative it is mu one. So situation whereby the alternative is greater, if you take a look at this now, what this implies is that the values you have in the non-hypothesis is less than the one you have in the alternative. Okay, now if you want to do that, the best critical region is going to be S bar greater than that. And if otherwise, at times you could have situation whereby the values in the non-hypothesis may be greater than the value in the alternative. So which means you actually conducting a lower T test. Of course, the critical region, the rejection region, is actually going to change into less than instead of greater than sign. Okay, so that's exactly what I mean. And based on the example that we've done before, okay, based on the example we've done before, we were considering upper T test, where the value in the known hypothesis is smaller than the one in the alternative. Take a look at this now. Okay, so we're gonna have that under the known hypothesis. We got that guy, and the X bar, we follow normal distribution, and it's gonna be the mean hypothesized in the non-hypothesis and the variance of the mean. Okay, so now with that, we actually want to figure out what C, because I told you we got to figure out what this particular C is. And to be able to do that, we are actually going to do that based on the level of significance that I call the probability of committing type 1 error. So the alpha, which is the probability of committing type 1 error, okay, is actually going to be the probability of X bar greater than C, because, this is, you got X bar greater than C when you were constructing, the best critical region using the Neyman Pearson Lemma idea. So the probability of committing the maximum probability of committing type 1 error alpha is going to be the probability of S bar, okay, greater than C, giving mu equal to mu naught. And what this guy is trying to say here, okay, the probability that the likelihood ratio test will be less than C. So it is synonymous with this guy here. So if I want to figure out this guy now, okay, so if I want to figure this guy out, so what I'm actually going to do, okay, because the random variable X bar here is follow normal distribution, by central limit theorem, the idea of a z-score is going to be used. Okay, so I'm actually going to interpret that as that. So I want to find the probability of z, okay, greater than. So I'm actually going to write that very c minus the mean of the c. Of course, we know the mean of the C, okay, divided by the standard deviation, which is going to be the square root of this guy, as you can see now. Okay, so if I have this guy now, don't forget, I need the values of mu naught, I need the standard deviation, I need the sample size, and I need this guy. So, and I told you this guy is here. Okay, the other time, we actually equated this guy, everything here, don't forget we equate that to Z alpha, right? So equating that to Z alpha, you can solve for C. Solving for C is actually going to be this guy. Okay, so which means if I want to figure out my C, I just need the values in the non-hypothesis. I need to check from Z table, then the standard deviation and the sample size. So take a look at that. So that is what we actually going to have as far as that is concerned. Okay, so the moment you have that now, okay, let me move to the next slide. Okay, so that's already decided. Okay, now if I want to figure out the probability of type 2 error, of course I can do that in two ways. I can compute the probability of type 2 error directly, or when I calculate the power, or what I'm just going to do is to subtract power from 1. Don't forget, I told you the other time, there's a relationship between them. Okay, so the probability of, if I want to focus on type 2 error, okay, now the hypothesis under investigation is going to be the alternative. Okay, so now because the type 2 error is a probability of not rejecting the non-hypothesis when it is not true. So which is going to be the probability of the likelihood ratio test is going to be greater than C, given that mu equal to mu1. Okay, the alternative is true, but we did not recognize that. We failed to reject it null. Okay, so what we're going to do, okay, when you go back to the critical region, okay, that we developed the other time, it was greater than, right? Do you see greater than, S bar greater than that? If I want to find the type 2 error, I'm going to use a complement of this. Okay, I'm going to use a complement of this, which is going to be less than. And that was why here you saw less or equal. The complement of greater than is going to be less or equal. Okay, so you're always going to do that if you want to find out the probability of type 2 error. So I'm actually going to pursue that within, Z architecture again. So I said that what I'm going to have this time around is just going to be the mean is going to be mu1 instead of mu naught. Okay, so take a look at that. And don't forget, if that happen, the whole of this is actually going to be, you have, so if I want to, interpret that now, it's going to be Z less or equal to Z alpha plus, this guy. Okay. And if I have that, I can equate the whole of this guy. Okay. The whole of that guy. So Z, okay. The whole of that guy to Z beta. Okay. The whole of, because when you're talking about type 2 error, okay, the type 2 error is actually, the probability of Z less or equal to Z alpha, okay, plus, okay, plus Z beta. Okay, just wanted to take note of that. So that is what we have here. So because that guy called Z beta, so I'm actually you know gonna write that guy. And the Z beta that we actually talking about is gonna be a -1. Okay, so it's going to be -1, plus negative. So we shall automatically we convert this guy to a minus in a way. Okay, so that is what you have right here. So what we can do now, okay, if we, based on this architecture, we can find the sample size. Okay, we can find the corresponding sample size. If I know the Z alpha, I know the Z beta, I know the mu1, the mu1, the mu naught, mu1, the sigma, then I'm only going to solve for n. So solve it for n now. So I'm actually going to have this expression. So when you take a look at this expression, it will give us an opportunity to know what is the minimum sample size required if I know, um, if I can control my type 1 and type 2 error. So here, for any desired level of, type 1 and type 2 error, and, the mu1 and the mu naught, the sigma, then I'll be able to figure out or the minimum sample size is actually going to be. If I know my alpha, when I can check the Z table, to be able to figure out the Z alpha. If I know my beta, I'll be able to do that. So that is the formula. Okay, so I think I'm going to go walk you through an example of that now. So if n equal to 25, mu naught equal to 0, mu1 equal to 1, sigma equal to 1, and alpha equal to 0.05, okay, determine the critical threshold C, the probability of a type 2 error, and the power of the test, So the moment you know the probability of type 2 error, you can also find the power of a test, which is going to be 1 minus that. So if you want to, you also find your C, right? You remember the other time, your C is actually going to be mu naught. I'm going to show you right now. Okay, you can see here, right? So you're just going to plug in the values given, okay, to be able to get the threshold. Okay, so that's exactly what we're doing here. So we got our very C now to be 0.329. Okay, and if it is 0.329, don't forget the rejection region was actually S bar greater than that. You know that we created S bar greater than that. So which is going to be X bar greater than 0.329 that we got. So the non-hypothesis should be rejected. So if I want to find the type 2 error on the other hand, so I'm actually going to go back to use this formula here. If I want to find the probability of type 2 error, okay, or what I just need is what is my Z alpha? I'm going to check that from the table, plug in mu naught, mu1, the sample size and the standard deviation. Then then whatever I got, I'm going to get the probability of Z less or equal to that, checking from a Z table. So, putting all of that now, okay, I'm actually going to arrive at this. And I'm checking this from the table now will give us the probability of type 2 error to be 0.0004. Okay, take a look at that. So, and then 1 minus that is actually going to be, the power of it says, the power here is so high because the probability of type 2 is very, very small. Okay, so the last example actually going to center on figuring out the sample size. Okay, you can be given mu naught, mu1, sigma, and the level of significance, and they really want to know how many observations are needed, to be made for the probability of type 2 error not to exceed 0.1. Okay, so if you want to do that, you're actually going to go back to the formula that we generated the other time. Okay, that has to do with this. You can see that's a sample size. Whenever you want to figure out the sample size, that is what you're going to use. So all what you just need to do is plug in the level of significance, check from Z table, plug in the beta, check from Z table, and plug in the values of mu1, the mu naught, and the sigma, and which is exactly what I'm doing here. You can see now. So like I've checked that from the table, they say the probability of type 2 error not exceeding 0.1. So, I check the Z 0.1 from the table is going to give me that. When I check in Z 0.05 from the Z table, it's going to give me that. And of course, the 1 and the 0 is just the values of the mu1 and the mu naught, and the sigma is already 1. And what we got here is 8.6. We normally round up, so that's going to be 9. So what we mean, 9 observations are actually going to be needed, for us to be able to, for the probability of type 2 error not to exceed 0.1. Okay, so that is the end of this lecture and end of chapter 10. Of course, Wednesday, we're going to start a new chapter 11. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.